A very good morning, good evening, good afternoon to all my dear students and friends. Welcome back to the 5th lecture under the NPTEL MOOC series, and the course is DADM, which is, as you can see, is data analysis and decision making 1, which basically is going to deal everything related to statistics and related topics. And as you know, this is the 5th lecture, which is would be the end of the first week. We have 12-week course, that is 30 hours lecture. Each week we have half an hour, and each week we will have basically 5 lectures. So, if you remember, we were discussing about probability, the concepts of probability, and how the concepts of probability can basically be extended to understand different type of probability distribution functions, probability mass functions. I will come to those topics in more details. So, probability of an event. So, what do you mean by event, what we mean by an experiment, and what we mean by probability, and where the actual concept of probability comes from, considering it is actually related to frequency and relative frequency, we will discuss that. So, probability of an event is defined as a quantitative measure of uncertainty of the occurrence of the event. So, say for example, if you have a dice and all the faces are marked from 1 to 6, and the probabilities or the chance or the frequency in the long run for any one faces coming is equal, and that is they are unbiased. So, we will say the probability of getting number 1 or 2 or 3 or 4 or 5 or 6 when you roll the die, when you are playing the game of Ludo, is 1 by 6. Or say for example, if you have a coin, unbiased coin, and if you toss it, the relative frequency or the frequency in the long run, or the probability of trying to get either the head or the tail, or if the faces are marked as blue or red or black or red, whatever it is half. Now, whenever you are dealing with probability, you should think of the concept that probability is basically the relative frequency in the long run. So, consider that you have you are doing an experiment. Consider the very simple one, you are tossing the coin and you do it 100 times. So, say for example, then it is an unbiased coin, and the number of faces which is coming as head is say for example 55, and number of faces which is coming as tail is 45. Now, again you consider, so obviously in that case the frequencies are as given as 55, 45, and the corresponding relative frequencies are 55 by 100, 45 by 100, which is 0.55, 0.45. Now, you do the next experiment again, and you again toss it at 100, and consider now the heads and tails in the respective numbers is now 60 and 40. That means, the relative frequency is 0.6, which is 60 by 100, and it is 0.4, which is 40 by 100. Now, you keep repeating it. So, the next time the corresponding relative frequency of head and tail is 0.7, and then for tail is 0.3, corresponding to next time when you do it is basically 0.5, 0.5. Other again you do it, say for example is 0.51, 0.49, next time you do it, say for example is 0.4 and 0.6, and consider it continues. So, what actually you will get in the long run, if you basically keep repeating it, then the averages of these averages, average means basically the relative frequency which you have is in the first case 0.55, 0.45 or 0.4, 0.6, or say for example 0.51, 0.49. So, in this case, if you basically keep adding them and trying to find out the averages of their average in the long run, for the probability for the head or the relative frequency of the head would come out to be 0.5, and similarly the relative frequency or the probability for tail would also come out as 0.5. So, objective probability based on the game of chance, and which can be mathematically proved or verified, we can do that. If the experiment is the same for two different persons, then the value of the objective probability would remain the same. It is limiting, is basically the limiting definition of relative frequency, as I mentioned. That means, if you keep repeating the experiment, the relative frequency in the long run as the actual number of experiments which you are doing goes to infinity, that value is basically the probability. Example, like finding out the probability in getting the number 5 when you roll the fair die. In the long run, say for example, the actual probability would be total number of 5s which are coming divided by the total number of such throws you are doing should actually tend towards 1 by 6. But in any case, if you do it, say for example, you roll it 600 times. So, it need not be that in each and every such experiment which you do, the probability or the relative frequency of getting number 5 in each case would be 100 by 600, which 1 by 6. It may differ, but in the long run the relative frequency or the actual average of the average should tend to basically 1 by 6. Subjective probability on the other hand is the definition based on personal judgment, intuition and subjective criteria. It is the value which will change from person to person. So, example, one person sees the chance of India winning the test series with Australia high, while the other person will say that the chances of India winning the test match against Australia is average, or another person may say is low. So, basically subjectivity is the point where the individual set of information, individual judgment would basically be coming in a very big way in order to basically have some information about subjective probability. But in the case of objective probability, it will be a very well defined mathematical formula based on which you are going to study and understand what is probability. For a random experiment, so that means when you are doing an experiment where the outcome, before you get the outcome, it is unknown, but once the outcome is available, you know it, but obviously that would be amongst the set of such possible outcomes which is possible. For a random experiment, we will define that each outcome is basically a sample point. So, say for example, when you roll the die, the sample points are 1 or 2 or 3 or 4 or 5 or 6. Now, if I define an experiment, that is the experiment is that when you get the even number only, then the collection of the sample points which is 2, 4 and 6 would basically give you the information about the experiment. If I say that I want to do an experiment where the number is less than equal to 4, then the sample points would be the point number 1 or plus 2 plus 3 plus 4, because it is less than equal to 4. So, whenever you are saying in a sample points would be defined by omega I, where I is basically equal to the number of such the sample points which you have. It can be infinite also, remember that. I will come to the experiment or the examples later on, and we will denote that the probability of getting that sample point is given by small p suffix I, depending on the case that what does I denote. So, say for example, if I am rolling the die and the probabilities are equal, that means it is an unbiased die, in that case the probability of getting number 1 is P 1, which is equal to 1 by 6. Probability of getting W 2, which is number 2, is equal to P suffix 2, which is 1 by 6. Probability of getting the number 3, where W 3 is equal to 3 is equal to P suffix 3, small p suffix 3 is equal to basically 1 by 6. So, in this case it will continue. But in case, say for example, if I say that the corresponding probabilities when you are tossing the coin, the corresponding probability of getting a head is, say for example, 2 by 3 and the probability of getting a tail is 1 by 3. In that case, when W 1 is head, the probability P 1 is equal to 2 by 3, when W 2 is equal to tail, the probability is equal basically is equal to 1 by 3, which is P 2. P means capital small p suffix 2. So, depending on the experiment which you have, you will analyze and say that the collection of the sample points which basically gives you the experiment A, we are using a symbol A to denote the experiment, is basically what the actual probability for that event is. So, say for example, we are saying for an unbiased die, if you roll the coin and if you want to find out that what is the probability of getting an even number, then W's corresponding to that event would be W 2, W 4, W 6, and the corresponding probabilities are 1 by 6, 1 by 6, 1 by 6. Then the corresponding overall probability for that event will be 1 by 6 plus 1 by 6 plus 1 by 6. So, here we will denote the capital P W I, which is small p I, is the probability of occurrence of the sample point W I, and the probability of A is the probability of the occurrence of the event, where the event is given by the conglomeration of all the sample points which are corresponding to that event A. So, the event A can have basically infinite set of points, we will come to that later on. And obviously, if you take all the sample points which makes the universal set, so obviously it will mean the corresponding probability of that universal set would be 1, and on the other hand the corresponding probability of the null set would be 0. Suppose there are two dice with faces 1 to 6 and they are rolled simultaneously one after the other or at the same time. This rolling of the two dice could constitute our total random experiment. How it is? Let me specify that. So, in that case the overall sample space or the total universal set would be, in one case consider what are the outcomes. The outcomes can be, the first one is 1, that means of the die, and the second one can be either from 1 to 6. In the other case, it can be the first one is 2 and the outcomes for the second one is 1 to 6. Similarly, for the third case, fourth case, fifth case and sixth case. So, if I consider all of the different type of combinations of the sample points, your actual outcome would be as denoted. The first one would be 1 comma 1, second one would be 1 comma 2, so on and so forth till the last one where we will have 6 comma 5, which where the outcome for the first die is 6 and the outcome of the second die is 5, and the last one will be where the outcome of first die and the second die is 6 comma 6. We define the event in such that the outcome for each die are equal in one simultaneous throw, then the experiment would be given or the event A would be given, where we want to basically find out what the experiment is, that if the outcomes for both the dice are same. So, it will be 1 1, then it will be 2 2, then it will be 3 3, then it will be 4 4, then the 5 5 and 6 6. So, obviously, the corresponding probabilities would be 1 by 6 plus 1 by 6, 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6. So, we are basically trying to 1 by 36, because my apologies, 1 by 36 because the outcomes are 1 and 1. So, obviously, the outcome of getting a 1 in the first die would be 1 by 6 and getting a number 1 in the second die is 1 by 6. So, it will be 1 by 36. Similarly, getting 2 2 would be 1 by 36. Similarly, getting 3 3 would be 1 by 36. Similarly, for 4 4, 5 5, 6 6, each of them would be 1 by 36. Hence, the probability of getting the event where the numbers are equal on the dice which are rolled would basically be, we will be counting 1 by 36 6 number of times. So, if you check here, the first value P 1 means 1 1 in the first and the second die. The 8 1 will basically mean we have 2 2 in the first and the second die, 3 3 in the first and the second, 4 4 in the first and second, 5 5 in the first and second, 6 6 in the first and second. So, hence the total corresponding probability is 6 by 36. Suppose a coin is tossed repeatedly till the first head is obtained. So, in this case you will understand what I have been saying, that the overall number of such sample points can be infinite. Now, if you note down the experiment, you want to do it and toss a coin repeatedly till the first head is obtained. So, in this case what the outcomes can be, it is in a head and you stop the experiment. In the other case, if the first outcome is tail, then you will continue, consider you get a head in the second throw, then you stop it. So, if it does not happen in the second throw, what is the next possible sequence? The possible sequence would be, you get a tail in the first, you continue, you get a tail in the second, you continue, you get a head in the third and you stop. Then if you do not get a head in the third, what are the possible sequence? It will be tail for the first, tail for the second, tail for the third, head for the fourth, stop. If it does not stop, then it will be, there would be tail, head, one tail, second tail, third tail, fourth tail, fifth head, stop. So, in this overall sequence, obviously you will have such infinite sequences, hence the overall set or the number of sample points which we will have for the experiment would be infinite. So, let me denote it, how what I mean talking about. So, in this case the universal set would be, the first sample point would be a head, you stop it, second sample point would be a tail and a head, third one would basically be a tail head, fourth one will be 3 tails and a head, and so on and so forth. So, the sample points are a head, as I said, a tail and head. So, a tail head, a tail head and continues. Now, if we define the event such that we want to basically have at most 3 tosses are needed to obtain the first head, and also consider that what is the probability of getting each and every sample point. So, the sample point where you get a head in the first trial is basically half. The sample point where you get a head in the second trial and a tail in the first trial would be half into half. The sample point where you get a head in the third trial and a tail in the first two would be half into half into half. Similarly, for the fourth case it would be half to the power 4, then half to the power 5, half to the power 6 and so on and so forth, it will continue. So, in that case the probability of the sample points are P 1, which is half, P 2 is half to the power square, P 3 is half to the power cube, P 4 half to the power 4 and continues. So, in this case if you want to find out that at most 3 tosses are needed to obtain the first head, then obviously the experiment would be a head, at most 3 tosses. So, it will be head, it will be a tail head, and the last case would sample point would be tail head. So, in that case the corresponding probability of the overall event would be, for P 1 it is half, P 2 is half to the power 4, P 3 is half to the power 3. So, you will add all of them and the value comes out to be 7/8. So, the classical definitions of probability, under this definition we consider the following: the sample spaces are finite. That means, remember that means that the number of sample points which constitute the overall sample space is finite. All the sample points are of equally likely, that means the probabilities are same, that they have equal probability of occurrences or equal relative frequency of occurrences. Hence, trying to find out of the values for the event or the values for the overall sample space is very straightforward. So, in the case when we want to find out that when you are rolling the dice and what are the probabilities of getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6 is all are equal probabilities 1/6, the sample points are finite, and hence finding out the overall sample space or an event is very straightforward. So, this is the classical definition of probability. Consider this: in a club there are 10 members, of whom 5 are Asians and the rest are Americans. A committee of 3 members has to be formed and these members are to be chosen randomly. Find the probability that there would be at least 1 Asian and at least 1 American in the committee. So, if there are 1 Asians and 1 Americans and you want to basically have 3 members, it can be 2 Asians, 1 American, or 1 Asian and 2 American. So, the total number of cases you will have is basically 10C2, and the number of these cases where you want to basically have the combination would be given as this. So, let me check. So, it would be, you want to check 3 1. So, obviously, it would be 3. Yes, just give me 1 minute. So, this will be my mistake, this would be 10C3, because you have 3 different positions to fill up and the total common number of combinations which you can do would be 10C3. So, that will come in the denominator, and the number of cases actually favoring that committee would be what is 1 Asian, 2 Americans, or 2 Asians, 1 Americans. So, what would the combination would be? If there are 5 members each, so in this case there are 2 Asians, 1 Americans, and the next case is 1 Asian and 2 Americans. So, the total corresponding probability would be, this value comes out to be 100. So, 100 divided by 10C3, which is 120. So, the value comes out to be 10/12. Consider the next experiment. There is a box containing 10 colored balls, out of which 4 are red, 4 are blue and 2 are white. So, if you draw a ball at random, what is the probability that is a white ball? So, obviously, if you are doing it for the first time and this concept of replacement or non-replacement does not come, then the probability of getting a white ball would be, you have 2 whites. The total number of balls, which is basically 4 plus 4, which is basically plus 2 is 10. So, you will find out the corresponding probability and then basically conclude the experiment. So, finding out the actual number of frequency of getting a white ball would be that you will have, either you will pick the first white or you can pick up the second one also as white. That means, there are 2 balls, you will pick up any one of them. Now, if you draw 2 balls consecutively and with replacement, then what is the probability that both the balls are red? So, if you pick up 2 balls and the first one is red. So, obviously, 4 are red and the total number of balls you can pick up is 10. So, the corresponding probability can be found out. But remember one thing, if you draw it consecutively with replacement, it means that you have drawn the first one as red, noted it down, kept into the box. So, the number of red remains 4, number of total balls remains 10. So, obviously, the corresponding probability in the second draw also remains the same. But now, if I ask the third question, if you draw 2 balls consecutively and without replacement, then what is the probability that the first is blue and the second is white? Or say, for example, continuing the same way as we did for the second example, what is the probability of drawing 2 balls consecutively red if you draw the first ball and do not replace that? In that case, the number of balls which you have, number of such red balls you will have on the first trial would be 2 balls out of the 10. Then when you pick up that red ball, find it out and then replace it. That means, we will have only 1 ball to be picked up which is red, but also you should note that the total number of such pickings you can do from the total number of balls is not now 10, it is basically 9. So, obviously, the corresponding probability when you picking up with replacement and without replacement will change. If you draw 2 balls consecutively and without replacement, then what is the probability that the first is blue and the second is white. So, but it will change here in this case, because the number of such blues which you can pick up in the first picking is 4, total number of balls is 10. So, obviously, you can find out the corresponding relative frequency and the probability. But there is a slight change when you do it with replacement, when you are picking up the second as white. So, here the first one is basically blue. So, obviously, white has not been affected. So, the second picking up which you do would have 2 whites, but the interesting part is that the total number of balls from where you are picking up the white is now 9 and not 10, because you have picked up one and basically removed it, that means without replacement. So, this concept should be clear. So, if I say that, say for example, if you are picking up 3 balls one at a time without replacement, and you want to find out that what is the probability that you will have all 3 whites. So, the first one is white, that means you have 2 balls out of the 10 you pick up that white and you remove it, then there is 1 ball out of 9 you remove it, but the last case you do not have white obviously, but the total number of balls has now reduced by 2, which is basically 8. We will consider the axiomatic definition of probability. Under this definition we consider the following: the sample space is infinite, sample points are not equally likely, which means that the total number of sample points which basically makes the total sample space are infinite number, and obviously, the corresponding probabilities of each sample points need not be finite. So, suppose that we are going back to the example which we did. Suppose we continue with the example 2 which we have just discussed, and we define the event B that at least 5 tosses are needed to produce the first head. So, in that case what we have is that the overall sample space is now, it is basically head. If we get a head we stop, if we do not get the head in the first row we will basically have a tail and a head. If we do not get a head in the first 2 it will be tail tail head. If you do not get head in the first 3 it will be tail 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 head, and it will continue accordingly. Now, in that case the corresponding sample points would be given by, as I mentioned, is a head, then the second sample point is tail head, third sample point is tail tail head, and so on and so forth. Now, the corresponding probabilities of the sample points is that if it is a head in the first and nothing and you stop experiment is basically half. If you get a tail and a head, the corresponding probability is half into half, which is half to the power square. In the case when you have to do the head in the third picking, it will be tail tail head. So, the corresponding probability half to the power 3 and so on and so forth. So, if I want to basically have at least 5 tosses are needed to produce the first head. So, at least 5 tosses means that you will have either 5 or 6 or 7 or 8 and it will continue till infinity. So, the overall probability would be 1 minus P 1, minus means you will basically first add up. P 1 means that you get the head in the first, P 2 means you get tail head, P 3 means you get tail tail head, P 4 basically means that you get 3 tails and a head. So, obviously, you will add up all this probability P 1, P 2, P 3, P 4, add it up and basically subtract from 1 and you get the corresponding probability which is for B. 2 fair coins. So, consider this 2 fair coins are tossed simultaneously and such simultaneous tossing is repeated till you get 2 tails. What is the probability that you need at most 2 such simultaneous tossing to achieve our objective. So, if you are basically simultaneous tossing and you want to get 2 tails together. So, obviously, it would mean that head tail or tail head and head head are not the combination. So, obviously, only the combinations are tail tail. So, in that case the corresponding probabilities would be, if you get a tail tail, it is probability of half into half, and the corresponding complementary set would basically be head tail, tail head and head head, which basically is also equal to half to the half into half into half. So, obviously, in that case half into half means that basically means for tail head, another half into half would be for head tail, another half into half would be for the head and the last half into half would be for the case when you have tail. So, if you continue doing it in this way, you can find out the corresponding probabilities and solve this problem. Now, theorems in probabilities for any event A and B which is there in the overall sample space, the overall corresponding probability of A is always between 0 and 1 inclusive. That means, the probability of A can be 0 also, probability of A can be 1 also. If A is a subset or a proper subset of B, then the probability of A is always less than equal to probability of B, because probability is always increasing, it cannot decrease, it can be 0, but it cannot decrease. So, the universal set or the trying to find out the universal of two events which is A and B is given by probability A plus probability B minus a probability A intersection B. So, what we are doing is this. So, this is A, this is B, I apologize, sorry for that. So, in this case, let me use the black one. So, this P A is all the red one. So, it will be red here, P B the blue one, and if I consider another color, say for example, green, for ease of understanding, let me give the word a green. Yes, use a bold color, it's coming out to be yellow. Yes. So, green, this is the one. So, you will understand that you want to find out the probability of A intersection B, you have to find out the probability of A, find out the probability of B, and the intersection would basically be subtracted. So, obviously, if the intersection is null set, it will be only be addition of that. The probability of an A complement, considering the event has been divided into two parts or the universal set is A n and A complement, would basically the probability of A complement would be 1 minus probability of A. The third the second last point is obviously the probability of the overall universal set is 1, because if this is the universal set, so obviously overall probability here, I am not marking it, for the overall box is 1 and probability of the null set where there is no element is 0. So, with this I will end the 5th lecture and continue more discussion about probability in the 6th and the corresponding lecture. Thank you very much and have a nice day.